Hello everyone and welcome to video number 5 in the 3-phase circuits course. In this video we are going to cover delta load connections. So we are going to explore how to calculate phase and line currents. We are going to have an example and we're going to assess this example using MATLAB Simulink. Let's start. So we have delta connection as you can see here. So I presume now that the source is delta as well. So we have the voltage applied to the load VAB is the phase voltage equal line voltage in this case. So phase or line voltages are VAB equals V angle delta, any angle. VBC will be V angle delta minus 120. VCA will be V angle delta plus 100. What about the currents? So we have phase current, which is a current going through the impedance. So the phase current is I angle theta, and definitely phase B and C, because we have balanced system, will be shifted 120 degrees from this theta. What about the line currents? So the line currents equals in magnitude √3 the phase current and lagging the phase current by 30 degrees. So I capital A will be √3I angle theta minus 30 degrees. So I capital B will be √3I angle theta minus 30 degrees minus 120, and definitely I capital C will be √3I angle theta plus 120 minus 30 degrees. But how do you calculate the phase current? And from the phase current you can calculate the line current. So if we have the impedance Z equals R plus JXL, again Z in magnitude will be √R square plus XL square, and phi equals tan inverse XL over R. So don't forget the brackets please. And if the load is R minus JXC, so this amplitude will be √² plus XC square, but phi equals tan inverse minus XC over R. So to calculate the phase current, I small a will be the voltage, phase voltage in delta equals the line voltage, VAB over Z. So that one is V angle delta over Z angle phi, so equals I angle theta. So in this case, theta equals delta minus phi. And remember, for the load power factor, cosine theta V minus theta I, which is cosine delta minus theta, which is cosine phi, which is the impedance angle, which is identical or similar to the star connection, but now we are going to have that one for currents, not voltages. Let me remind you about the star. The star, we have phase voltage and line voltage equal √3 the phase voltage and leading the phase voltage by 30 degrees. But here we have line voltage equals phase voltage and line current equals √3 the phase current and lagging by 30 degrees. Let us take an example. A 3-phase delta connected load shown in the figure is supplied by an ABC sequence balanced 3-phase delta connected source with a phase voltage of 220 volt 50 Hz. We need to determine the phase voltages, line voltages, phase currents and line currents. So the question here is not clear because that one is delta connected. If there is any difference between phase voltages and line voltages, no. So VAB equals 220 angle 25. VBC will be 220 angle 25 minus 120. So that one will be 220 angle minus 95. And VCA will be 220 angle 25 plus 120 equals 220 angle 145. Someone said that. Can I write that one minus 240? Yes, no problem at all. Phase voltages equals line voltage in delta connection. What about the phase current? So we are going to write IA equals VAB over Z. And we have the same impedance like the star connection example. So that one will be 220 angle 25 over Z, which is 10 angle 53.13. So the current is 22 angle minus 28.13 ampere. So definitely IB will be the same current in magnitude, but minus 28.13 minus 120, and IC equals 22 angle minus 28.13 plus 120 ampere. What about the line current? So the line current will be here IA, IB, IC. So I, for example, A equals √3I and angle, if that one is theta, minus 30 degrees. So that one will be 22 √3 angle minus 28.13 minus 30. And I capital B will be the same magnitude, but the angle will be the same angle here, theta minus 30 degrees minus 120. I capital C will be the same magnitude, but theta minus 30 degree plus 120. What is the phasor diagram of the delta connected load looks like? As we can see here, we have three voltages, VAB, VBC, VCA. They are shifted 120 degrees from each other. Regarding the phase current, we have 22 ampere shifted from the reference. The reference has angle 0, so VEB is shifted 25 degrees and IA, small a, is 28.2, lagging. So the current, phase current is lagging the voltage, phase voltage or line voltage for the delta by 53.2, where the power factor is cosine, 53.2 is 0.6 lagging. Regarding the line current is lagging the phase current by 30 degrees, as we can see here. So from the reference, something like 58.2. So that one will be something like 58.2 from the reference. So the green arrows are the line currents. They are 120 degrees apart. So what are the results from the MATLAB Simulink? If we look here, we have phase currents 22 ampere and the angle minus 28.2, and the currents for phase B and C, they are shifted 120 degrees and they have the same amplitude. Regarding the line current, they are 38.1 and minus 58.13. So if we multiply 22 by root 3, you are going to find that one 38.1 ampere. And if you have minus 28.2 minus 30, where the line current lags the phase current by 30 degrees, that one gives you something like minus 58.13 or 0.2. Regarding the voltage is the same. Line voltage equal phase voltage, 220 volts, and the angle will be 25, shifted by minus 120 and plus 120. What about the waveforms? Here we have three voltages, VAB, VBC, VCA. Don't forget that these values are RMS, RMS, RMS. So the voltage here, peak value is 311. 311 over root 2 gives you 220 volts. So that one, RMS value is 220, peak value will be 311. So the voltage VAB will be leading the zero or the reference point by 25 degrees. 120 degree from this point to this point, another 120 degree here, or 240 to this point. Let's look for the current waveforms. So the right side here we are going to measure the current, the left side we are going to measure the voltage. So the voltage with respect to the reference point is positive 25 degrees, this one. But the current is lagging this reference point by 28.13 or 28.2, which is a solid red color. For the dashed line, that one is the line current, peak value 53.9, and lagging the phase current by 30 degrees. From the 0 point, it will be 58.2. 53.9, so 53.9, if you divide it by root 2, that one gives you 38.1 ampere. And 38.1 ampere, if you divide it by root 3, give you this value, which is that phase current value. It's time now to go to the Simulink platform to check the delta connected load. But again, I'm not going to set up the model because I explained that one before in the induction machine course chapter 5 video number 2, dynamic simulation using Simulink. Let's go. As you can see here, this is a circuit we want to simulate, delta connected load. Each impedance is 6 plus j 8 ohm and the supply voltage is 220 volt angle 25. Supply voltage to the load. So we are going to apply the voltage across the load terminals 220 angle 25. So if we click to one of these loads, so RLC branch, so I'm going to choose RL, the resistance is 6 ohm and the inductance should be in Henry, so that one is 8 over omega, XL equals omega L if you remember. So I'm going to divide that one by omega 2 by F and the supply frequency is 50 Hertz. So I'm going to repeat that one for phase B and phase C. So now we can connect that one as a delta. The end of phase A will be connected to the start of phase B. The end of phase B will be connected to the start of phase C. And the end of phase C will be connected to the start of phase A. I can do the opposite. Now going to the source, I'm going to do the same. I'm going to take the start of phase A to the end of phase B, the start of phase B to the end of phase C, the start of phase C to the end of phase A. But unfortunately, when we are going to run, we are going to have an error. Let's check. So we have error in this source. So these sources will not accept circulating current. So we need to find another solution. So what is the solution? Either we're going to use a three-phase transformer, star delta transformer, to feed this load, or we are going to have this source as a star connection, but we are going to modify the values. I'm going to use the second solution. Let's look here. I'm going to connect that one as a star connection, but the voltage here should be adapting the voltage of the delta connection. So I need a voltage across the delta, 220 volt, and that one is a line voltage equals phase voltage regarding delta, but that one is a line voltage for the star connection. So if I click here, I need to modify that one to be 220 volt multiplied by root 2 to have the peak amplitude, but I need to divide by root 3 to have that one as a phase value with respect to the delta. So when I'm going to have that one 220 volt root 2 over root 3, that one is phase voltage. The line value for that one will be 220 root 2, which is applied to the delta. Let me repeat again. So if we have the voltage across the delta, I needed 220 volt. That one is line equals the phase for the delta. Regarding the star, that one is a line voltage. So I need to modify that one to have that one as a phase voltage. So inside this one, I'm going to modify that one to 220 root 2 to have the peak divided by root 3 to have it as a phase. Regarding the angle, I need that one to be 25, and that one is phase voltage applied to a delta, but that one is a line voltage from the star. And we know that the line voltage from the star is leading by 30 degrees, so I need to modify the phase voltage by this 30 degrees, so 30 degrees minus 25, so that one will be minus 5 here. So if we have minus 5 plus 30 degrees, we are going to have here definitely the voltage 220 volt we need with angle 25. Let's check now. Run. The voltage applied to the delta is 220 volt, angle 25, and for phases B and C shifted 120 degrees. Regarding the line currents is 38.1 and the angles is minus 58.13 and shifted 120 degrees. Phase currents inside the load will be 22 ampere and the angle is minus 28.13 and shifted 120 degrees. So please take care when you are going to deal with the delta that the source should match the required voltage here. So let's return back to our slides. Let us summarize the delta connection like what we did in the star connection. So we have here line current lags the phase current by 30 degrees. The line current equals root 3 the phase current. The line voltage equals the phase voltage. The angle between phase voltage and phase current is the load impedance angle, which is the power factor of the load. For balanced load, the circuit can be solved per phase. What will I watch in video number 6? In video number 6, we are going to cover three-phase power. See you in the next video.